Hello and welcome back to another VMK in the game development series. In this video, I'm going to show you how to implement the remaining structure, which was going to contain all the PolyH data that's saved inside the Caligari file. So let's just jump right in. Inside Visual Studio, I just want to give you a quick recap of what we've done up till now. You'll remember back in scene.cpp, we created a load Caligari file function. And inside here, we created this Caligari file class, which went and parsed all the data inside of the Caligari file. After it's done, I've said that there's going to be more code placed in here, and we're not going to be touching this code in this video. So what we're going to do is go inside of the parser here, and you'll see that the parser is broken down into a couple sections here inside the while. We have PolyH, material, and shader box data. We've already covered how to create the structures to save this and this inside memory, but now in this video we're going to be going in and creating a structure to save all the PolyH data. And if we just expand this, you'll see down here somewhere I created a class called CaligariPolH. So that's what we're going to be creating in this video. So to get started with that, let's go into our object library and create those two files that we need. And we also need the .h. Okay, starting up at the top, we include core.h, plane.h, Vector2, and Vector3.h. I'll talk about these a little bit later, but we're going to be using them, so that's why we need to include them at the top. Now you remember when I created the Caligari file class, I said that all the structures that the Caligari file is going to contain is going to be saved inside this CaligariPolH.h file. So that's why you see the Caligari header, Caligari chunk header, Caligari chunk name, Caligari chunk axis, Caligari chunk transform, and Caligari material. These are all the same structures that we created whenever we made the parser project that just parsed the Caligari file. So what I did is I just cut and pasted those structures right into here inside the CaligariPolH.h file. Oh, and don't forget the Caligari face structure down here as well. I don't think I used this structure before in the Caligari parser project, but we will need it in here. So what it's going to do is it's going to save the material ID number that is used per face, and each face is going to be comprised of 3 vertices. So 3 of these values are going to be the vertex indices, and the other 3 are going to be the UV indices. And this is described inside of the Caligari document, which I outline what is inside each of the Caligari file chunks. Alright, so here's the actual class itself. We have a constructor and a destructor. The constructor takes the same parameters that the other classes took, but now I also added the error handler. This is important because the CaligariPolH class is going to be doing a lot of processing to figure out how to render things inside OpenGL. And because of this, there could be a few possibilities where some errors show up, so I need a mechanism to be able to display these errors to the user. So to do that, I pass in the pointer to our error handler so that we can go in and anytime we have an error, we can just either log it to a file or display it to the screen as well. We have some functions here, setName and getName. This will save the name of this PolyH structure. We have setTransform and getTransform. This will just save the transform data that is loaded in from the Caligari file. And we also have addVertex, addUV, and addFace. These are the functions that we'll call anytime we pull a vertex, a UV, or a face data out of the Caligari file. Finally, down here in the member variables, we have the ID numbers, we have a pointer to our error handler, and then we have containers to store all the vertices, all the VVs, and all the faces. And we also have a pointer to the name that we want to associate with this PolyH data, and we have the transformation matrix, which is a 4x4 matrix right here. Okay, so now let's go into the CPP file and start implementing this class. Okay, then down inside the constructor, we have our ID number and our parent ID number. Because these get saved inside of the constant member variable here, we need to use the special notation with the brackets for each member variable, and then this goes before the curly brace located right here. We save our error handler. We initialize our name to be null because we don't have a name by default for PolyH data. And we also initialize the transformation matrix to be identity. So you notice we have ones across the diagonal and zeros everywhere else. Then we have our destructor. Our destructor is going to clean up any memory that gets saved inside of the name. So if it's null, then this won't do anything, but later on when we assign a name to this variable, then this would basically clear up any memory that gets allocated using the new operator. Next up we have save name and get name. Now the allocation of the memory that's going to get stored for the name is actually happening outside of our class, and you'll see this back inside the Caligari file parser. Let's see if I can pull it up here quickly. Here we go and create this Caligari chunk name. We allocate new memory for the name, and then we get the name and we null terminate it. So as soon as we do that, we've used the new operator right here to give memory for this name that we're going to use. Then down below, let's see here, we have set name. So if everything here goes okay, which is basically creating this structure that will store the poly data, we then go and replace all the spaces with underscores. If all this is okay, then we go and save the name inside of our structure. As soon as we save the name, we don't need to copy the memory that was allocated up here. Instead, we use that memory directly, so that's why we allocate our pointer inside of our class directly to whatever's passed in here. So from now on, we are responsible for this memory. And that's why whenever we call delete, we need to delete the memory that is allocated with the name. Anytime we want to return the name to the user, then we just call getName, and then this will return the pointer that contains the name data for this PolyH. If this is still set to null, then this will return null, which means that if you go try to print it, you're not going to get anything onto the screen. Actually, I think you'll get garbage onto the screen. So you need to do also an error check to make sure that there is a name saved before you try to display to the screen. Okay, next up, let me just open this guy up here. We have, okay, so we just covered getName and setName. Let's do getTransform and setTransform. We're passing in a pointer to this Caligari chunk transform, and we need to save it inside of our 4x4 matrix, which is actually an array of 16 values. So we're taking all 16 variables here and saving the values that are passed in here into this function. So row by row, we're passing everything in. And oh yeah, remember that Caligari chunk transform is really a 3-row by 4-column matrix. It is assumed that the last row is 001 or 0001. So that's why you see here for every single value at the last part here, I already hard-coded the 0001 part. Now, if you want to get the transform, you'll call getTransform, and we return the address of the very first thing inside of this array. Then we can go in and use it however we need to render things onto the screen. One thing I should mention here is this setTransformation function is not going to give you what you expect. But I'll come back to this a little bit later. As a matter of fact, there's a lot of code that I've shown you so far that is not going to function the way you would anticipate it to function, but that's okay. I want to present this the way that I am because any person that's going to be programming things will probably take this approach. And I want to show you the pitfalls that come about by taking the following approach. So anyway, just be aware that this transformation matrix is not the one that you really want in the end. But again, we'll come back to this a little bit later. Okay, and then we have our add vertex, add UV, and add face. And they're all pretty much the same. We just take the Vector3 value, the Vector2 value, or the Caligari face value that gets passed in, and we're pushing them onto the array, which contains all the vertices, all the UVs, or all the faces. And again, if I go back here, these are the 3 member variables that are arrays that are going to contain all the vertices, all the UVs, and all the faces. And I think that's it. So let's just go and compile this. And we got some error message here. Cannot open Vector2.h. Okay, it appears that we haven't actually implemented this Vector2.h inside of our project. If we go under Math, we see we have a Vector3, but we don't have a Vector2. Well, we'll need a Vector2 because down here, all the UVs are a two-dimensional vector. So let's go in and actually implement this. I'm going to create a Vector2.cpp and a Vector2.h and just basically copy in all the data from Vector3 where we just strip out the Z component. So we're just going to leave the X and the Y. So we'll just quickly do this here. Okay, so here we go. We have our class Vector2. We have a constructor. If we don't pass in any parameters, we set the two components X and Y equal to 0. If we pass in an X and Y value, we just set those into our member variables. If we pass in a floating point array, we just take the first index and the second index and save those into our member variables. We have a destructor, which is defined in Vector2.cpp here. And we need to do this so that we don't get that compiler warning saying that there's no actual data inside of the CPP file. So I've placed a destructor inside CPP. We have our plus equal operator, which just takes this vector and adds to the components, X and Y. We have the minus operator, which just takes the negative here and subtracts the two vectors. We have the minus operator, so we just take the negative of the X and Y and return that. We also have minus equals, which we take this vector and subtract whatever we're passing in here from ourselves. We have the multiplication operator, so we just multiply a constant by the two components inside of our member variables. We have a normalize function, which basically normalizes our vector to have a length of equal to 1. So we do a check here to make sure that we're not dividing by 0, and if we're not, we just go and normalize, divide by the magnitude, and then we save that inside of our member variables. We have a function to check to see if this vector is 0. So if it is 0, we check to see the absolute value of X and absolute value of Y. If they're both less than this epsilon 5, then we return true, otherwise we return false. Our member variables are very similar to our Vector3, where I created this union between an array of two values and a structure which contains the two floating point numbers. And that's basically it. So again, that's the .h, and the CPP file just has our destructor. Alright, so let's now go back into here, and let's see if we can build this project now. Okay, I did see some errors. Okay, we have a warning here that truncated from double to float. Our pi value is defined as a double because we didn't specify an f at the end of the definition. So let's just go in here, and we have our pi value. Well, that's interesting. I noticed that our pi value is defined inside core.h. Let's move this out of here. Let's get rid of the pi value here, and because pi is really used with a lot of math stuff, let's put it inside of our math library. Let's see here, under generalmath.cpp, or sorry, not cpp, but .h. We have some constant definitions here, so here's our epsilon 5 for 0 comparison. Let's just add pi in here. So it's going to be a constant floating point number. It's called pi, and the value is going to be 3.141592654, and we have an f at the end here. The precision of your pi value doesn't matter too much, but that's what I'm going to be using there. You want definitely more than just 3.14 to give you better accuracy when you're doing rotations. Okay, so that should get rid of that one thing. Now we also have an error here saying it doesn't know what pi divided by 180 is. Pi divided by 180 is 0.017453292, and we stick an f at the end to make sure that this number is actually a floating point number. So we'll just add that inside generalmath.h as well. And anything else? Let's see if we can build now. Looking good. And we still failed with one error. Okay, we have unresolved external, and the function it's looking for is setColor. That means that there's probably something wrong with the Caligari Map1 class. So let's just go take a look there, see what we have. We do have a setColor function definition here, but it appears that we forgot to implement it inside of the CPP. Yeah. Okay, not a problem. We can just go in here and implement it right now. So here we go. We have the function called setColor, and we pass in red, green, blue, and an alpha. And what we're doing is we're just taking those 4 components and saving them inside of our member variable mf4color, which contains red, green, blue, and alpha. All right, let's go and compile that and see if we can build. All right, that's it. We're now done parsing the Caligari file and saving all the data inside memory. So we're basically done all of this, and if we run this now, we should see absolutely no difference from what we had before. So let's give it a try. Oh, it looks like cannot open resource models mech.cob. Well, that's probably because inside of our function that loads this guy, let's see where we go in here. Right here. So inside of initialize, we call load Caligari file, and we're saying let's load in this model. Well, this model right now doesn't exist. So let's go in and create this model and put it in here and see what happens. So here we go. I created a mech.cob file, dumped it into our resource models directory. So now when we go and run our program, it'll be able to find it. But you'll notice that there's no mech on the screen. Why is that? Well, because we haven't actually created any code to render our cob files. All we've done is we've taken all the data out of the cob file and saving it in memory. But we haven't actually created a mechanism to go and somehow render this data. That's what we need to do next. And to get started with that, what we need to do is create a new kind of geometry. You'll remember that back inside of our object library, anytime we created a new object, we always inherited from this class. So we created a geometry box, a geometry cylinder, geometry flat grid. All of these inherit directly from geometry, which contains these functions here. Actually, it's a prototype because it's a purely virtual functions. We have an update and we have a render OpenGL function call. Well, now we need to create a new kind of geometry that will be able to render any kind of Caligari file. The quickest and easiest way that I thought of doing this is to create a generic geometry class which can be used for any kind of geometry we want to render. And the way this is going to work is very similar to, let's see if I can find it here, font. You remember inside of our font we had a texture which we loaded, and we loaded in all the characters in for this texture. But then when we wanted to render text to the screen, we only rendered the specific characters that we were interested in. And the way we knew which ones we wanted was basically using this structure here, using this generated lists that OpenGL supports. So what we're going to do is we're going to use the display lists for our new geometry. And the overall mechanism is this. Anytime we load in a Caligari file, we're going to create a thing called compiled geometry. And the compiled geometry is going to contain all the code necessary to render the item that we loaded in from the file. The compiled geometry is going to be stored inside one display list, so then when we need to go and render it, all we do is just call render this one display list, and then everything gets rendered appropriately. The appropriate materials are used, appropriate textures are used, and all that other stuff. So this wrapping function is going to be called GeometryCompiled. So let's go inside the object lib and implement this right now. Object lib right in here. Okay. At the top, we need to include geometry.h because you see here our class is inheriting from geometry. We have a constructor and a destructor. And then we have two functions here called startRecord and stopRecord. Then the two required functions that we need is update and render OpenGL, so we have those here as well. And for our member variables, we only have one thing, and it's just a number. And the number is going to be storing the display list number that is associated with this compiled geometry. So now let's go inside of the CPP and see how this is going to work. The functions in here are actually very simple. There's only, like, I think one line of code per function because all the functionality to make this work is going to come in from a different location. But let's just go through here and write out what we have. We have our constructor, which goes in and creates one new display list to be used by this geometry. So we call GL genLists, and we say we want to use one guy, and that guy is going to get saved inside of our member variable. When we go and call the destructor, we need to deallocate all the memory that OpenGL used for this display list. So we need to call GL delete lists. We specify which list we want to delete, and this list is only size 1, so that's why we specify the second parameter as 1 here. Then for startRecord and stopRecord, what I do is I call GL new list. So here we're saying, okay, I want to use this list here, which is the same one that we initialized up here, and we're saying we want to compile all the following data. So whenever we're creating this compiled geometry, we're going to call startRecord at the very beginning. Then this is going to start compiling everything into this display list. At that point in time, we can then start calling all the OpenGL functions to render our object to the screen. Once we're done, we need to call stopRecord, which is just going to call GL endList, and it's going to finish off this display list, which was started up here. So these two have to work in unison so that you save the geometry appropriately. Then we have our update, which doesn't do anything. We just skip over it right now. And then we have our render OpenGL. This is the guy that actually renders everything to the screen. The stuff up here is only used to compile all the OpenGL calls into one sort of function. And the function we use to render everything is called GL call lists. And we specify the list number we want to render, so that's the same guy here that we were compiling into. And as soon as we call this, then our object is now rendered to the screen, all in one go. So very simple and very easy to use. Now let's go and compile this, make sure that's okay, and that's it for this video. So what we've accomplished is being able to save all the data we need inside memory, and we've created a structure now so that we can go in and render things to the screen. But to be able to render them, we need to be able to go back into, where was it, inside scene here, and inside of this function, load Caligari file, we'll be loading in the Caligari file, parsing it. This will save all the data inside memory, and then we're going to close the Caligari file off. So we're completely done with the Caligari file. We're no longer interested in it. The following code here, which we'll be adding in the next video, is going to be going in and creating all the individual pieces that we need to create nodes inside of the scene graph. These nodes will then be able to be used with this GeometryCompiled class so that whenever we go and render things, we can stick in the compiled geometry class directly into the scene graph, same way we've done everything else before, and the flow of our program will continue being the exact same that we had before. Okay? So that's it. Come back for the next video where we can actually start implementing the methods to render our Caligari files.